Imagine you're writing like this massive 100,000 word sci-fi epic.
Right, a huge project.
Yeah. And in chapter 2, you establish that your protagonist is deathly allergic to copper.
Okay, I see where this is going.
Well, you get to chapter 40, and they are thrown into a copper mine. If you are using a standard AI to help you co-write, it will have completely forgotten that allergy.
Oh, absolutely. It'll just cheerfully write a scene where they touch the walls and feel completely fine.
Exactly, and it just destroys your continuity. So today, we are going to build a machine that never forgets.
A very specific machine, actually.
Yes, we are looking at a highly specific cutting-edge mission for you, the listener, in the year 2026. We're building a completely local, highly personalized LLM pipeline engineered specifically for long-form novel writing.
Right, a system that basically acts as your co-writer, your continuity editor, and, your lore keeper.
But, and this is the defining constraint here is the hardware.
Yeah, we are not renting time on some massive corporate cloud cluster.
No way. We are doing this entirely on a standard home computer. Specifically, one equipped with just a 12-gigabyte VRAM GPU.
Something like an RTX 3060, which honestly is the standard for most people.
Which honestly sounds impossible at first glance, right? I mean, we're in 2026. The AI landscape is completely defined by agentic workflows now.
Right, those autonomous systems that, plan, retrieve data, reason over it, and execute tasks.
Exactly. And people are running these on massive 80-gigabyte A100s. Squeezing an agentic, highly creative fiction pipeline into 12 gigs of video RAM.
It's tough. It requires absolute architectural mastery, so you don't just melt your graphics card.
It really demands zero waste. Like every megabyte of VRAM has to be accounted for.
Yeah, we have to meticulously select the foundation model, carefully compress it without destroying its memory, which is hard, and inject your specific authorial voice into the weights.
Plus, we have to build a local vector database for its long-term memory, all under that 12-gigabyte ceiling.
It's a huge mission. But we have a really incredible stack of sources for this deep dive to guide us through it.
We really do. We're analyzing the latest 2026 benchmark reports from daily.dev and Watson Out. Plus, we've got this dense, super critical ACL anthology paper on long context quantization.
That paper is a lifesaver, honestly. We also pulled technical documentation directly from Parlance Labs, LoRaX, and Proxy Tech Support.
And to keep you out of legal trouble, we're examining copyright research by Xuzi Chen.
Don't forget the real-world creator experiments, like Lorelei Noble's custom RG pipeline, and some pretty brutal lessons from Reddit users in the hardware trenches.
Right. So we have the map. Okay, let's unpack this. Because if we approach this sequentially, the immediate bottleneck is the engine itself.
Yeah, before we can talk about memory or style, we need to actually load a large language model into the GPU.
And the daily.dev 2026 guide establishes a pretty strict rule for consumer hardware, right?
It's non-negotiable, really. You have to prioritize memory availability over raw parameter count.
I really want to challenge the premise of parameter count driving everything, though, because, I mean, the industry has been obsessed with it for years.
Oh, totally. People used to think you couldn't write a coherent sentence without a 70 billion parameter model.
Right, but 70 billion parameters, even at, like, the lowest usable precision, takes roughly 40 gigabytes of VRAM just to load the weights.
Yeah, on a 12-gigabyte RTX 3060, it simply will not boot. The application just crashes instantly.
So daily.dev points us specifically to the 8 to 14 billion parameter tier.
Which is honestly the sweet spot for a 12 GB card. Let's break down the math a little bit.
Please do, because the math is where people get tripped up.
So a 14 billion parameter model, if we use standard 4-bit quantization, takes up about 8 to 9 gigabytes of your VRAM.
Leaving you with, what, 3 to 4 gigabytes of free space?
Exactly.
Right.
And you desperately need that remaining space for the KV cache.
Which is basically the model's short-term memory of the conversation you're having with it, right?
Right. That and the external tools we're going to plug in later.
Yeah.
You can't max out the VRAM on just the model weights.
Okay, so looking at the daily.dev recommendations for that specific 8B to 14B class, Qwen 3 14B immediately jumps out to me.
Oh, Qwen 3 is a powerhouse. It has this massive reputation for multilingual work. It natively understands over 100 languages.
Which is wild. So if you're writing a novel that incorporates heavy world building with constructed languages, or even just translating a manuscript, it's perfect.
It is, and it also excels at coding, which strangely translates very well to structural outlining.
Wait, really? Coding helps with writing a novel?
Yeah, it's fascinating. A model that understands the rigid logic of a Python script is remarkably good at maintaining the structural pacing of a three-act narrative.
That actually makes total sense.
Yeah.
But what if your novel relies heavily on complex deductive logic, like a locked room mystery?
For that, the daily.dev guide suggests DeepSeek R1 Distill 14b. The pedigree on that model is insane.
I saw that the foundational 32B version scored a 72.6% on the AMI math benchmark.
Which is notoriously difficult. We're talking about reasoning capabilities that were strictly for supercomputers just 3 years ago.
So if you need a model to verify if the orbital mechanics of your spaceship battle actually make sense, the distilled 14B version is your go-to.
It brings that intense logical rigor right down to a consumer GPU. However, logic and prose are very different beasts.
Right, a model that calculates orbital mechanics perfectly might write dialogue that sounds like a dry textbook.
Exactly. If your primary goal is the actual texture of the prose, the atmosphere, the emotional resonance, the Skywork data points us toward the News Hermes 13B model.
Yeah, I was looking at that. News Hermes is specifically fine-tuned on high-quality human literature and role-play data sets, right? Not just Wikipedia.
Right, it understands subtext. It knows how to write a conversation where two characters are discussing the weather, but the underlying tension is actually about a betrayal.
That's the nuance you need for fiction.
Yeah.
But we should probably acknowledge a hardware fallback here.
Good point. Some listeners might be looking at their system specs right now and realizing they don't even have a 12 GB dedicated GPU.
Yeah, they might just be on a standard laptop with like 8 gigabytes of shared system RAM.
For that scenario, the daily.dev guide explicitly highlights 5.4 Mini. It's a 3.8 billion parameter model.
And it runs efficiently in roughly 2.5 to 2.8 gigabytes of memory. That's incredible.
It's a total lifeline for ultra-low hardware. But for our 12 GB mission, we have a major hurdle regarding the type of model we select.
Okay, yes. The Watson Out review spends a massive amount of time analyzing obliterated or uncensored models, and I have a fundamental issue with this.
I thought you might. A lot of people do.
Well, the term uncensored AI just carries so much cultural baggage. You know, people immediately associate it with sketchy content or malicious code.
Right, the dark web stuff.
Yeah. If a user is just trying to write a traditional fantasy epic, why go out of their way to find an obliterated model? It feels like an unnecessary risk.
That hesitation is incredibly common. But it really misunderstands how safety alignment actually works on a mathematical level.
Okay, walk me through the math then. Why is it a problem for fiction?
So, standard AI models are trained using RLHF reinforcement learning from human feedback. During that phase, the model is penalized for generating violence, harm, or intense psychological distress.
Right, the safety training.
Exactly. The model literally develops a refusal circuit in its neural network, a mathematical shortcut to immediately shut down if it detects specific keywords.
Right, so apply that to fiction writing. Fiction is fundamentally driven by conflict.
Exactly. If you're writing a thriller, your antagonist might commit a crime. In a fantasy epic, there are battles and tragedies.
So when you ask a highly aligned model to generate a scene where a detective discovers a crime scene, the refusal circuit just triggers.
Yes. It looks at the words blood or murder and categorizes your request as a safety violation.
I've actually experienced this firsthand. I asked a model to brainstorm a scene where a villain threatens a protagonist.
And let me guess, it refused.
It returned a paragraph saying, I cannot generate depictions of intimidation. Perhaps the characters could resolve their differences through constructive dialogue.
It's infuriating, right? It completely ruins the pacing and the creative flow. We call that the flinch response.
Constructive dialogue with a Sith Lord. Great advice, AI.
And sometimes it's even more subtle. The model might not refuse outright, but it'll subtly alter the tone, make the villain less menacing.
Or wrap up the scene with some unearned, preachy moral conclusion.
Exactly. Obliterated models solve this entirely. They just do not have that flinch response.
Okay, so the Watson Out benchmark points to a very specific obliterated model that fits our 12 GB constraint, the IBM Granite 4.18B.
Specifically, the heretic version of that model.
Right, heretic. I need to understand how this is created, though, because they didn't just ask the model nicely to stop refusing prompts, right?
No, and they didn't spend millions of dollars retraining it from scratch either. They used a technique called surgical tensor editing, specifically the heretic V1.2.0 method.
Surgical tensor editing. That sounds intense. How does it work?
Instead of retraining, researchers map the model's internal vector space. They isolate the exact neural pathways that activate when the refusal circuit triggers.
Let me make sure I'm visualizing this correctly. You have an 8 billion parameter model, a massive matrix of numbers.
Very massive, yeah.
And they somehow find the exact handful of numbers responsible for the "I cannot fulfill this request"
Yeah.
response.
Out of billions of tensors, they locate 1,826 specific ones, and they edit just those 1,826.
Wow, that is literally microscopic neurosurgery on an AI.
It really is.
Yeah.
By zeroing out or modifying those specific connections, they remove the safety refusal without touching the areas responsible for grammar, logic, or prose.
And the Watson out data backs up how clean that surgery is using KL divergence.
Right, the heretic model has a KL divergence of just 0.029.
To clarify for anyone who hasn't stared at machine learning stats all day, KL divergence measures how much the probability distribution of the outputs changed, right?
Exactly. If the score is high, it means the surgery basically gave the model brain damage. It might stop refusing, but it forgets how to spell.
So a score of 0.029 means the underlying intelligence is virtually untouched.
The practical result is astonishing. The granted heretic 8B has a refusal rate of just 1.2%. You can write the darkest, grimdark fantasy, and it just follows your instructions.
And because it's only an 8B model, it uses roughly 5 gigabytes of VRAM, sitting perfectly within our 12 gigabyte constraint.
We do need to mention the models we have to walk away from, though, the sacrifices we make for 12 gigs.
Yeah, Watson out highly praises the Huiquin 3.635B model and a dense 27B model by a researcher named Wang Zhang.
That Wang Zhang model is fascinating because the creator is incredibly transparent. They openly advertise a 10% refusal rate.
So you know exactly what you're getting, but we have to admire these from afar, right?
Unfortunately, yes. A 27B model needs at least 17 gigs of VRAM. A 35B needs over 20. Trying to load them on a 12GB RTX 3060 will just give you an out-of-memory error.
Adhering to the 12 GB limit forces a lot of discipline, but it also highlights this profound shift happening in 2026.
It really is a democratization of power. An independent author can run an uncensored 8 billion parameter intelligence in their bedroom.
With no internet connection, a brainstorming partner that never judges your themes, never sends your plots to a corporate server, and costs nothing in API fees.
It is absolute creative sovereignty. But getting the engine onto the hard drive is just phase one.
Right. To make these 14B or 8B models fit into that tight VRAM space, we have to compress them.
And this brings us to a massive hidden trap that software developers rarely encounter, but that will absolutely destroy a fiction writer.
Because novels are massive documents, and this trap is all about the precision problem over a long context, right?
Yes. This is perhaps the most critical technical hurdle in the entire pipeline. It's meticulously detailed in that recent ACL anthology paper.
Let's break down quantization first, because it sounds like quantum physics, but it's really just aggressive rounding.
That's a great way to put it.
Imagine you're painting a hyper-realistic portrait. You have a massive palette with 16 million specific shades of color. That represents a 16-bit floating point number.
Which is the native high-precision format these models are trained in.
Right. You can capture every subtle shadow, but a 16-bit model takes up too much memory. So quantization forces you to throw away that massive palette and use an 8-color watercolor set instead.
The watercolor analogy captures the mechanism perfectly. You can still paint the portrait, the grass is green, the sky is blue, but you lose the intricate shading.
You compress the model into a 4-bit space to save memory at the cost of precision.
And in the AI world, the consensus has always been that 4-bit quantization, the 8-color palette, is perfectly fine.
Right, if you ask a 4-bit model to write a Python script or an email, you barely notice a difference. The logic holds up over short distances.
But the ACL anthology paper evaluates something completely different. They tested these models on inputs exceeding 64,000 to 128,000 tokens.
Which is the length of an entire novel manuscript.
Yes. And their findings are devastating for novelists relying on heavy compression.
The researchers found that 8-bit quantization formats like FP8 or GPT-5.5 is nearly lossless, right?
Exactly. Performance drops by a negligible 0.2 to 0.8%. The model retains its intelligence.
However, when you compress down to 4-bit precision like AWQ-4 or specifically BNB-NF4, the degradation is catastrophic over long contexts.
The numbers in the paper are brutal. The BNB-NF4 format caused an average performance drop of almost 7% across all tasks.
And the specifics are what matter to us. They use 2 benchmark tasks. No CHA, testing reasoning over book-length texts, and CS4, evaluating constrained story generation over long distances.
They measured the results using a metric called book score, which mathematically analyzes story coherence.
And under 4-bit precision, the book score just plummets.
The model literally loses the plot. If you feed it a 50,000-word draft and ask for the next chapter, a 4-bit model will forget character motivations established in Chapter 1.
It contradicts the world building, it introduces plot holes.
All because it can no longer hold the full narrative architecture in its compressed memory.
I really want to dig into the mechanical why here. Why does the model get stupid only when the document gets long?
What's fascinating here is it comes down to a mathematical mechanism called rope-E, rotary position embedding.
Okay, rope-E. Explain that for us.
When an LLM reads text, it doesn't read it sequentially like a human. It processes all the tokens simultaneously in a massive vector space.
So to understand that the dog bit the man is different from the man bit the dog, it has to mark the positions.
Right. It applies a rotation to the word vectors. Rope-E literally rotates the mathematical representation of the word in a high-dimensional space by a specific angle.
So the rotation angle is essentially a timestamp for the word.
Precisely. Now, introduce 4-bit quantization. You are rounding off the numbers used to calculate that rotation angle.
Which introduces a tiny error. But in a short document, that error is microscopic, right?
Exactly. Over 1,000 tokens, the model can still clearly distinguish the positions. But over 64,000 tokens, those tiny rounding errors compound exponentially.
So by the time it tries to calculate the position of a word in Chapter 40, the rope-E rotation is completely misaligned.
The model's sense of narrative time just collapses into static.
And the ACL paper points out an agonizing detail for international writers. The one-ruler tasks show that if you write in a non-English language, the degradation is up to 5 times worse.
Yeah, that multilingual penalty is harsh. And the reason is tokenization. Most LLMs have tokenizers optimized for English.
So a single English word equals 1 token, but a word in Japanese might be split into 3 or 4 separate tokens.
Exactly. Because non-English languages require far more tokens to express the same idea, they hit that rope-E degradation threshold much faster.
Okay, so we have a massive dilemma regarding our 12 GB limitation.
Well,
The daily.dev guide tells us 4-bit is the holy grail for squeezing a 14B model into our GPU. But the ACL paper scientifically proves 4-bit destroys long-form fiction coherence. How on earth does a writer actually survive this contradiction?
you have to abandon the idea of a single, static workflow. You survive by implementing a dynamic, hybrid approach to model loading.
Meaning you swap models based on the task.
Yes. When you're doing close-up, immediate drafting, say, writing a tense 1,000-word dialogue exchange where immediate reasoning is key, you load the 14 billion parameter model in 4-bit.
Because it fits in VRAM, it's highly intelligent, and over 1,000 words, those rope errors don't matter.
But the moment you need the AI to read your whole manuscript to check for pacing issues or plot holes, you have to unload the 14B model.
And switch to what?
For full manuscript analysis, you switch to a smaller model like the IBM Grand Heretic 8B, and you run it in 8-bit precision, like the FP8 format.
Okay. An 8 billion parameter model in 8-bit precision takes about 8.5 gigabytes of VRAM. It still fits.
It fits, and because it's running at 8-bit, the rope rounding errors are virtually eliminated. It can read 100,000 words perfectly.
I have to push back heavily on this workflow, though. You're telling a writer who is in a creative flow state to constantly stop, purge their VRAM, boot up a different terminal, load an 8.5 gigabyte file, and wait for it to initialize.
It does sound disruptive.
It sounds like a total workflow nightmare just to check a plot point.
It would have been a nightmare 3 years ago. But in 2026, the local software ecosystem has adapted. Tools like LM Studio or Olama can hot swap models in the background via API calls.
Really? So the software handles the unloading and loading automatically?
Yes. If your 12 GB GPU is paired with a modern NVMe Gen 4 or Gen 5 solid-state drive, loading an 8.5 gigabyte model takes 3 to 5 seconds.
Wow. Okay, so you literally configure your writing software so drafting prompts route to the 14B, and review prompts flush the VRAM and route to the 8B.
Exactly. The delay is less time than it takes to take a sip of coffee.
Okay, if the software automation handles the heavy lifting, I can see how the hybrid approach works. You use the 4-bit 14B lens for the intricate close-up character logic.
And you use the 8-bit 8B lens for the wide-angle structural overview. It's a brilliant way to cheat the hardware limitations.
Okay, so we've bypassed the memory trap, but we face a new problem. If you ask either of those models to generate a scene right now, they will produce text that sounds like generic AI prose.
Grammatically perfect, heavily structured, and entirely devoid of human soul.
Which is the fastest way to ruin a novel. You don't want a generic ghostwriter. You want a digital clone of your own specific voice.
You want the AI to use your vocabulary, your pacing, your unique dialogue structures.
And this brings us to customization and the real-world blueprint provided by Lorelei Noble.
Lorelei Noble is a great example. She refused to accept generic AI outputs and is actively building a highly customized pipeline trained directly on her own life's work.
Her poetry, her novels, her song lyrics, she's forcing the AI to adopt a highly specific tone that belongs entirely to her.
It's the ultimate goal. But once again, we slam right into that 12-gigabyte brick wall.
According to the Parlance Labs deep dive, a full fine-tune of an LLM requires an immense amount of memory, right?
Yes. Updating the actual weights of all 8 billion parameters requires storing the weights, optimizer states, gradients, and activations.
So if you try to run a full fine-tune on a 12 GB GPU,
The script will crash with an out-of-memory error before it even processes the first sentence.
so this is where the magic of LoRa comes in, low-rank adaptation, and specifically QLoRa.
Yes. I know Laura gets treated like a magic wand in forums, but we should break down what is mathematically happening.
Please do. I need a deep mechanical breakdown of this.
Okay, a neural network is essentially a massive collection of weight matrices grids of numbers that multiply together. Normally, you adjust every single number when training.
But LoRa introduces a radical shortcut. It completely freezes the original model.
Exactly. It locks the massive grid, which immediately saves huge amounts of memory because you no longer track gradients for it.
Okay, so the original brain is frozen. How does it learn your writing style?
Lorelei injects 2 tiny new matrices alongside the frozen ones. Let's call them matrix A and matrix B.
And these are much smaller.
Matrix A shrinks the data down to a tiny bottleneck, what we call the rank, and matrix B expands it back out.
So if the original model has a matrix of 4,000 by 4,000 numbers, matrix A might only be 4,000 by 16.
And matrix B is 16 by 4,000. So instead of trying to update 16 million numbers, you're only updating about 128,000 numbers.
That is a massive reduction. Think of them as a thin layer of sticky notes placed directly over the massive frozen encyclopedia of the base model.
The base model knows the English language. The sticky notes tell it to use your specific adjectives.
And QLoRa takes it even further by loading that frozen base encyclopedia in 4-bit quantization, right?
Yes, squeezing it down to fit in VRAM, while you train the sticky notes in 16-bit precision to capture the subtle nuances of your prose.
That is how you achieve fine-tuning on a home computer, and the tool that makes this accessible for authors is Axolotl.
The Parlance Labs documentation highlights how Axolotl wraps all the complex Hugging Face scripts into a single, manageable command line interface.
You just configure a YAML file, point it at your data, and hit run. But the data format is crucial. The docs specify using the alpaca format.
Right, you can't just paste a 300-page novel in. You have to curate it into pairs, an instruction and an output.
So you reverse engineer prompts for your own scenes. Like the instruction might be, write a tense, atmospheric dialogue scene between 2 characters who mistrust each other.
And the output is the actual 500-word scene you wrote in your last book.
You build a data set of maybe 200 to 500 of these instruction output pairs, feed it into Axolotl, and it outputs an adapter.
A file that's often less than 100 megabytes, containing the mathematical essence of your writing voice.
The Parlance Labs document stresses a point every writer needs to hear. Data quality absolutely dominates hyperparameter tuning.
Oh, people waste weeks messing with learning rates, hoping it will fix messy outputs. If you feed the AI your unedited first drafts, it learns to write like your unedited first drafts.
Quality over quantity is the rule, but the true architectural brilliance emerges when we look at the Lorax documentation.
Yes, we don't just want one generic author voice adapter. We are building a tag pipeline.
Explain how Lorax handles this, because it sounds like we're building a multi-personality AI.
We are building an ensemble of specialists. You extract your world-building encyclopedias and train one adapter strictly on environmental descriptions.
And then extract rapid-fire arguments and train a second adapter on snarky dialogue.
And a third on scene summaries for outlining. You have 3 separate sticky notes.
But how do I use them without overloading my 12 gigs of VRAM? Loading the base model plus 3 adapters has to crash the GPU, right?
This is the genius of Lorax. It manages dynamic batching and adapter swapping entirely within the GPU's ultra-fast SRAM.
The base model stays loaded once, and the adapters are so small they take up almost 0 space.
When you send a prompt, you include a specific tag.
Like dialogue, make the two smugglers argue about the broken hyperdrive.
Lorax reads the dialogue tag, instantly applies the dialogue sticky note, generates the snarky response, and unloads the sticky note.
And your next prompt could be description. Describe the rusted exterior of the ship, and it swaps to the environmental sticky note.
You have a team of specialist co-writers operating sequentially within the same memory footprint.
It's incredibly elegant. However, there's a massive pitfall regarding how you train those adapters, and it comes from a brutal lesson in the visual AI world.
Ah, the Z-image turbo disaster on Reddit.
Yeah, a user tried to train a LoRa for image generation on a 12 GB setup. To save memory during training, they used a heavily distilled, compressed base model.
And the results were disastrous. They got plastic results and a total loss of photorealism.
Does this warning apply directly to our text pipeline?
Absolutely. In text generation, we call this manifold collapse. If you run Axolot to train your prose LoRa on a 14B model crushed to 4-bit.
The AI can't accurately map the subtle linguistic nuances.
Exactly. The resulting adapter will feel plastic. Your prose will be formulaic, repetitive, and stripped of its unique cadence.
So what's the solution? A 14B model barely fits in 12 GB at 4-bit. How do we train a high-quality LoRa?
You return to the 8B model for the training phase. You load the 8B model in the highest precision possible 8-bit or 16-bit and extract your LoRa adapter using a solid mathematical foundation.
And once it's saved to your hard drive, you can apply it to a 4-bit model later for drafting.
Yes. The lesson is never compromise on precision during the actual training phase.
Don't build a house on a compressed foundation.
Got it. Okay, let's step back. We have the localized 8B and 14B engines. We bypass the ropey precision trap. We have dynamic LoRa adapters via LoRaX.
The AI sounds exactly like you, but it is still fundamentally an amnesiac.
Right. We solve style, but not long-term memory. If I establish in Chapter 2 that a bartender has a mechanical left eye and 50 pages later the crew goes back.
The AI is not going to remember the mechanical eye. The KV cache simply cannot hold the entire novel simultaneously. It needs a permanent memory bank. This is the domain of RAG retrieval augmented generation.
But the proxy tech support documentation makes it clear. Basic RAG architectures are entirely obsolete for complex fiction in 2026.
Let's clarify why basic RAG fails. People think RAG just means uploading a PDF. It chops your novel into random paragraphs, converts them to vectors, and stores them.
When you ask a question, it searches for vectors that mathematically match the keywords, grabs a single paragraph, and shoves it into the prompt.
Which is completely disconnected from narrative logic. If basic RAG chops your text in the middle of a vital climax, the AI only retrieves half the conversation.
It might retrieve a quote of someone crying, but misses the previous paragraph explaining why. The AI is fed context devoid of meaning.
So proxy tech support pushes us towards modular and agentic RAG, and the foundation is the local database itself, LanceDB.
For a 12 GB constraint, LanceDB is perfect. It's an embedded columnar vector store.
Why LanceDB specifically? Why not a standard SQL database or a row-based vector store?
Columnar databases store all data of a single type together, unlike row-based, which store every piece of data about a single entry together.
So when searching through millions of lore vectors, a columnar format lets the system scan only the relevant mathematical dimensions.
Exactly, drastically reducing CPU RAM and VRAM overhead. It runs directly within your application process locally.
That saves memory. But how do we solve the chunking problem? How do we ensure LanceDB isn't cutting conversations in half?
The pipeline must utilize Markdown-aware splitters and semantic chunking. The ingestion script analyzes the structure for paragraph breaks, dialogue tags, and chapter headings.
So a complete semantic idea of full conversation or physical description is kept together as a single vector chunk.
Yes, but the retrieval is where the real 2026 magic happens. The documentation points heavily to GraphRag.
I really want to spend time on this because GraphRag fundamentally changes how an AI understands a fictional universe.
GraphRag moves beyond simple keyword matching. It constructs a knowledge graph. It processes your lore offline and extracts triples, a subject, a predicate, and an object.
Give me an example of a triple in a fantasy context.
Subject, the Crimson Crystal. Predicate, powers. Object, the Imperial airships.
The system extracts thousands of these relationships and builds a network graph, nodes and edges connecting every character, location, and item.
And it uses community detection algorithms to group these connected nodes into summaries.
So if I prompt my pipeline with a complex question, how does the newly discovered flaw in the magic system affect the local economy in the capital?
A basic RAG would just search magic flaw in economy and return a random paragraph. It wouldn't know the answer.
But GraphRag traverses the edges. It knows the flaw affects crystals. Crystals are mined in the north. The guild relies on exports, and the city taxes the guild.
Exactly. It retrieves this entire chain of relationships and feeds a comprehensive community summary to the LLM.
It essentially acts as a dedicated continuity editor who instantly reads your series wiki and hands the AI a dossier before it writes the scene, locally.
And an agentic pipeline goes one step further to ensure absolute accuracy using self-RAG and adaptive RAG.
These are reflection mechanisms, right? How does an LLM reflect on its own output? Does it read what it wrote after the fact?
It evaluates the data during the process. When GraphRag retrieves that lore dossier, the LLM uses the hidden critique token to grade the information.
Analyzing whether the retrieved facts actually answer your prompt.
If it finds the data is irrelevant or contradictory, it triggers a new search query before generating the first word of prose.
So if I ask it to write a scene with a character who died in Chapter 10, GraphRag pulls the character's file, sees status deceased.
The reflection token analyzes it, realizes the prompt is asking a dead character to speak, and flags the error to you instead of hallucinating them back to life.
It creates a closed-loop system of absolute narrative consistency. Style mimicked flawlessly, perfect memory maintained via GraphRag.
We have built a masterpiece. But this brings us to the final and most dangerous layer of our deep dive, the legal minefield.
Copyright. The research paper by Shuzi Chen maps out the severe copyright risks inherent in LLM generation.
Let's lay out the threat model. You're using your 14B model to write a scene set in a magical boarding school.
Because the model was trained on terabytes of internet data, there's a non-zero chance it accidentally outputs sentences that heavily mirror Harry Potter.
And if you publish that, you are committing copyright infringement regardless of intent.
Chen's paper outlines the first instinct the industry had to solve this: silo language models.
The concept is architectural purity. You build an LLM from scratch and only train it on public domain texts works published before 1928.
So a silo model has never read Stephen King. It's legally bulletproof.
Legally flawless, but practically useless. The utility drop is massive. It fundamentally lacks the vocabulary and structural understanding of modern prose.
If you try to write a cyberpunk thriller, it'll sound like an 1800s parlor drama, so silo models are out. How does a local author protect themselves?
We return to agentic workflows. Chen's paper details agent-based intervention. We add an automated copyright material detector directly into the pipeline.
Walk me through the mechanics of this detector. It utilizes an n-gram matching algorithm, right?
An n-gram is simply a contiguous sequence of words. The boy who lived is a 4-gram. The detector cross-references generated text against a database of copyrighted sequences.
Wait, I have to stop you there. The math is not adding up.
What do you mean?
We have a 12 GB constraint. We have an 8 GB LLM loaded, LanceDB running, LoRa adapters in the SRAM. How are we loading a massive database of every copyrighted book into that same 12 GB VRAM?
That is the crucial architectural distinction. The n-gram database does not run on the GPU.
It doesn't. Where does it go?
It runs on your standard CPU system RAM. System RAM is cheap and abundant. The LLM generates a paragraph in the VRAM, and before it's displayed, it's passed to the CPU.
Okay, so the CPU runs the match against a heavily compressed, hashed local database or queries an external API.
Exactly. It happens instantly in the background.
So if it flags a sequence of words that's too close to a protected work, does the agent just delete the scene?
The agent intercepts the text, packages it with a system prompt that says, rewrite this passage to eliminate similarities to copyrighted material, and sends it back to the LLM.
The AI rewrites the prose to be original, and only then is it presented to the author. It's an invisible legal safety net.
But the debate in 2026 goes both ways. How do you protect your own work?
Right. If I spend 6 months building my GraphRag lore Bible and generating a draft, how do I prove that I authored the architecture behind it?
This is where invisible 2026 watermarking technologies become absolutely essential. Chen highlights tools like MarkLLM, Waterwax, and PersonaMark.
Let's demystify watermarking in text. With an image, you change imperceptible pixels. With text, every word is highly visible.
This is entirely statistical. An LLM predicts the next token based on a probability distribution.
So if the sentence is, the knight drew his, the LLM calculates sword has a 90% probability, blade has an 8% probability.
And the watermarking algorithm uses a cryptographically secure pseudo-random number generator seeded by the hash of the previous token to split that vocabulary list into a green list and a red list.
And it artificially inflates the probability of words on the green list. Wait, won't that force the AI to choose weird words and ruin the nuanced prose?
That was the problem in 2023. But modern tools like Waterwax manipulate the marginal probability. The algorithm respects the entropy of the sentence.
So if a word is absolutely necessary for semantic coherence, the watermark doesn't intervene.
Right. But in areas of high entropy, with many valid synonyms, it consistently biases the selection toward the green list.
So across a 5,000-word chapter, there is a mathematically detectable statistical bias in the vocabulary choices, driven by a cryptographic key.
Chen's research notes these tools can embed a 140-bit cryptographic key. To a human reader, the prose flows perfectly naturally.
But if someone steals your manuscript, an algorithm can reconstruct the green lists and prove the presence of your specific 140-bit key.
And the key is remarkably robust. It survives paraphrasing, translation, and even being used as training data for a secondary model.
It proves that you, the architect, built the machine that generated the prose. Okay, we have covered an immense amount of ground. Let's recap this ultimate 2026 novelist pipeline.
We begin with the foundation model, the 8B Granite 4.1 Heretic, utilizing surgical tensor edits to ensure it never censors dramatic conflict.
We load that model in high-fidelity 8-bit precision, like FP8, to preserve the Roby embeddings, bypassing catastrophic long-context memory loss.
We inject your authorial soul into that model using axolotl, training low-rank QLoRa matrices on your best prose.
Then we deploy Lorax to dynamically swap those stylistic tags in the GPU's SRAM on the fly.
We ground the system in your fictional universe using LanceDB and GraphRag to map complex relationships, using self-rag reflection tokens to mathematically fact-check the output.
And finally, we run an automated n-gram matching agent on the CPU to prevent copyright infringement and secure your artifacts using Waterwax to embed an invisible 140-bit cryptographic signature.
It's a stunning piece of engineering. A closed-loop, hyper-intelligent, deeply personalized digital co-author running entirely on a home computer.
It respects your privacy and understands your world as well as you do.
If we connect this to the bigger picture, it leaves us with a profound question. If a local AI can mimic your prose via LoRa, recall your universe through GraphRag, and manage legal constraints,
Where exactly does the tool end and the author begin?
it suggests the art of writing is evolving. It might no longer be strictly about the physical act of bleeding words onto a blank page. The role of the author is becoming architectural.
It's about how elegantly you curate your training data sets, how precisely you define the edges in your lore graphs.
Exactly. How skillfully you conduct the dynamic tags of your own digital ghost.
The author becomes the architect of the mind that writes the book. You are designing the consciousness of your co-writer.
It's an incredible, empowering thought.
Going back to where we started, that pristine expanse of white isn't lonely anymore. The machine is built, the pipeline is primed.
It's just waiting for you to boot up the system, load the adapters, and start the conversation.
To everyone listening, it is time to fire up those 12-gigabyte GPUs and start building your ghost. Thank you for joining us on this deep dive. We'll catch you on the next one.